Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into a scale of power that begins with a flicker of lightning and ends with the birth of everything we know. A ladder of energy stretching from the smallest sparks to the most unimaginable explosions the universe can produce. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the universe's most powerful events together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Imagine, somewhere far away, farther than the moon, farther than the edge of our solar system, in a region where stars are just faint pinpricks of light. 2 neutron stars are circling each other. They are not large in appearance, no bigger than a city. If you could somehow hold one in your palm, though you couldn't, it would weigh more than every mountain on Earth combined. They orbit so closely that the very fabric of space is stirred like water in a whirlpool, each lap sending ripples of gravity out across the universe. These ripples are so subtle that when they arrive here, after travelling for hundreds of millions of years, they stretch and squeeze the Earth by less than the width of a proton. And yet, they carry the signature of something extraordinary. The final seconds before these 2 stars collide, releasing more energy in a single moment than the Sun will produce in its entire lifetime. It sounds impossible, but this is what nature does. What's most humbling is that we can trace this kind of cosmic power back along a line of smaller, more familiar events, things that happen here, on our little blue world. If you've ever watched a summer thunderstorm rolling in, you've seen energy move through air in ways that are both beautiful and dangerous. Lightning, that sudden fork of light, is the universe on a very small scale, doing what it does best, rearranging energy from one place to another in the fastest way it can. That's our starting point. A small spark, then a bigger one, and then bigger still, each step carrying us further into the quiet extremities of physics. Tonight, we'll travel slowly from the warmth of our own atmosphere, past the restless surface of the Sun, through stars that collapse and explode, into collisions that shake the structure of space itself. Along the way, we'll meet bursts of, like that last less than a heartbeat, winds that sculpt whole nebulae and explosions that can outshine galaxies. You might think of this as climbing a staircase where each step is not just a little taller than the one before, it's 100 or 1,000 times higher. By the time we reach the top, we'll be standing at the moment of the Big Bang itself, looking down that unimaginable drop and realizing that lightning and galaxy collisions are in some sense part of the same conversation. Of course, the difference is scale. Lightning here on Earth can be powerful enough to split a tree or start a fire, heating the air to a temperature hotter than the surface of the Sun. But in cosmic terms, it is a whisper, a faint rehearsal before the real performance. Solar flares, for instance, release enough energy to power the entire human civilization for tens of thousands of years. Yet they're still small compared to what happens when a massive star dies, or when 2 neutron stars finally meet. The strange thing is that no matter how big or small the event, the rules are the same. The same physics that drives the spark in a storm cloud also governs the jets of light that shoot from the hearts of galaxies. Nature has a way of repeating its patterns, changing only the scale, the setting, and the audience. That's part of what makes this journey comforting. The further we go, the stranger things will look, but their essence will still be familiar. I want you to picture that journey like drifting down a very slow river. We'll pass through places where the water is calm and the air is warm, then into stretches where the current grows faster, carrying us past landscapes that are harder to imagine. At first, we'll be in the gentle shallows, lightning, volcanoes, the warmth of the sun. But further along, the river will carry us into rapids of radiation, explosions and collisions that make even our sun look quiet. And finally, we'll flow out into the open ocean, the deep, dark expanse where time and space themselves were born. Even when we reach the most intense events, gamma ray bursts, black hole mergers, the Big Bang, will keep the pace slow. This is a series for sleeping minds as much as waking ones. No rush, no sudden jolts, just a gentle unfolding of the universe's most powerful moments, one after the other, like turning the pages of a book you already love. We begin here with the awareness that power is not just destruction, it's creation too. Lightning makes nitrogen available for plants. Solar storms paint aurora across the sky. Supernovae seed planets with the elements that will become oceans, mountains, and people. Even the collision of two neutron stars, violent as it sounds, is a kind of gardener, scattering gold and platinum into space, where, millions of years later, they might find their way into the hands of a jeweller on some quiet world. In the end, this journey is about connection. The gold in your wedding ring, the oxygen in your lungs, the heat in your coffee, all of it came from somewhere in this ladder of power. By climbing it in our thoughts tonight, we aren't just marvelling at what the universe can do, we're tracing the story of how we got here. And so, with the storm clouds gathering and the river of our journey beginning to move, let's take the first step. We'll start in the air above our heads, where the smallest of our cosmic engines lives, a flicker of light in a thunderhead, and see how even the tiniest spark can be the first chapter in a story that ends at the edge of time. If you've ever stood on a porch and watched a storm approach, you might remember that strange quiet that comes just before the rain. The wind pauses, the air feels heavy. Somewhere far away, a cloud is building an argument with the ground. Inside it, water droplets and tiny pieces of ice are moving up and down in rising and falling columns of air. They brush against each other, trading electrons the way strangers might accidentally exchange glances in a crowded street. Slowly, the cloud begins to divide itself into opposites. A top full of positive charge, a base full of negative. The ground, feeling this imbalance, responds in kind. Positive charges gather along rooftops, treetops and hilltops, pulled upward by the invisible tug of the cloud's electric field. You can't see this happening, but you might feel it in the prickle of hair on your arms, or in the metallic scent that seems to arrive out of nowhere. When the difference in charge becomes too great, the cloud and the ground make their move. A thin, invisible path of ionized air, called a leader, begins to snake down from the cloud. At the same time, an answering surge of positive charge leaps upward from the highest points on the ground. They meet somewhere in the middle, and in that instant the path is complete. The stored energy, held back for minutes or hours, now empties itself in less than 1,000th of a second. The lightning you see is not just one stroke, but a rapid series of pulses racing back and forth along that path, each one heating the air to temperatures over 50,000 degrees Fahrenheit, hotter than the surface of the sun. The sudden heat makes the air expand faster than the speed of sound, and the result is thunder. The sky's way of saying that two sides have finally reached an agreement. From a safe distance, it's beautiful. But up close, it's a reminder of how concentrated nature's power can be. A single lightning bolt might contain 1 billion joules of energy, enough to power a household for weeks. And yet, in the scale of the universe, it is barely a flicker. The lightning's journey from cloud to ground is only a few kilometers, but in that short space it manages to create light bright enough to see from miles away, and sound loud enough to echo off distant hills. Some lightning never reaches the ground at all. cloud-to-cloud strikes leap sideways across the sky, stitching different storm cells together in threads of white fire. Others strike upward, from the tops of thunderheads into the higher atmosphere, forming red sprites or blue jets, ethereal shapes that flash for less than a millisecond, too brief for the unaided eye to catch unless you're lucky. And there are places on Earth where lightning is more common than anywhere else, where the conversation between sky and ground never seems to end. Over the waters of Lake Maracaibo in Venezuela, storms form so reliably that sailors used to navigate by them. On some nights, the sky there flashes more than 200 times an hour, turning the clouds into a pulsing ceiling of light. Yet for all its drama, lightning does more than startle us or light up the horizon. It helps fertilize the planet. The intense heat of a lightning bolt breaks apart the nitrogen molecules in the air, allowing them to bond with oxygen and form nitrates. These fall to the ground with the rain, becoming nutrients that plants can use. Every flash is, in a sense, a tiny gardener, feeding the forests and fields. It is one of those rare cases where destruction and creation happen in the same instant. If you stand under a storm and think about it long enough, you might realize how much lightning resembles events on far grander scales. In a way, it is a miniature version of the forces that drive some of the universe's most spectacular outbursts. It builds up silently, it moves with sudden release, and it leaves behind both beauty and change. The mechanics, the build-up of energy, the sudden discharge, are echoed in solar flares, in supernovae, even in the meeting of neutron stars. The physics does not change, only the stage and the actors do, but we aren't rushing there yet. The river of our journey is still moving through its quiet early bends. Before we leave the Earth, we'll pause for a moment with the other powers we've made and encountered here. Powers born not in clouds, but in human hands and in the deeper workings of the Earth itself. Because while lightning is the most visible reminder that nature can move vast energies in an instant, we've learned to make our own brief imitations, and the planet beneath our feet holds forces that dwarf even those. It's worth noting, though, that lightning still humbles us. We've tried to control it, with lightning rods, grounding wires, and tall towers. But we can only redirect it, never stop it entirely. Benjamin Franklin's famous kite experiment in 1752 wasn't a test of whether lightning existed, but a way to prove it was the same kind of electricity we could make in a laboratory. The kite's wet string carried charge down to a key, and from there into a Leyden jar where it could be stored. It was a dangerous experiment, and Franklin survived partly by luck. In the centuries since, we've learned to measure lightning's currents, sometimes over 300,000 amperes, but we still can't summon it on demand. Perhaps that is fitting. There is something about lightning that feels better when it remains a little untamed, a little beyond our reach. It keeps us aware that we live in a world still full of sudden, unpredictable beauty. And as we step from this familiar flicker into the next rung of the ladder, we'll carry that awareness with us, into the heat of human-made fire, and into the deep rumblings of the Earth's own engines. A campfire is an easy thing to understand. You pile up wood, strike a match, and the storg, energy of sunlight trapped in those logs for years, comes rushing back out as heat and light. The crackle of resin, the slow curling of smoke, the way the flames lean and sway with the wind, it's energy being released in the most familiar way we know. A chemical reaction. Carbon meeting oxygen, and deciding they'd rather be together, giving off warmth in the process. Fireworks are a little faster, a little more dramatic, but still the same family of event. A sudden, colourful rearrangement of chemical bonds. It can feel spectacular, standing under a sky filled with streaks of light and pops of sound. But in terms of physics, it's still modest. The energy comes from the arrangement of electrons in atoms and molecules, and there's only so much you can get from that. For centuries we thought that was all there was. that matter was made of indivisible atoms and that the energy stored in them was mostly unreachable. But in the early 20th century, we learned something that changed the scale entirely. The atom was not indivisible, and inside its tiny nucleus was a storehouse of energy so vast that even a small pebble, if you could unlock it, could power a city. That idea, that mass itself was a kind of frozen energy, was captured in the most famous equation in physics, E equals mc squared. Energy equals mass times the speed of light squared. The speed of light is a big number. Square it, and it becomes almost unimaginably large. Multiply even a gram of mass by that, and the result is a figure in the trillions of joules. In other words, the matter in a sugar cube could, in principle, hold enough energy to run your home for centuries. We found two main ways to reach into that storehouse. One was by pulling heavy nuclei apart, nuclear fission, as in uranium or plutonium. The other was by pressing light nuclei together, nuclear fusion, as in hydrogen becoming helium, the way the sun works. Both release enormous energy because the products are slightly lighter than the starting materials, and that tiny difference in mass is turned entirely into energy. The first nuclear devices we made were fission bombs. They were devastating by human standards, their heat and blast changing cities in seconds. But then came fusion bombs, which used a fission explosion to ignite fusion fuel, multiplying the yield. The most powerful of these ever detonated was the Soviet Tsar Bomba in 1961. Dropped over a remote island in the Arctic, it produced a fireball 8 kilometers wide and a mushroom cloud that climbed through the atmosphere like a rising continent. Witnesses described it as a second sunrise, so bright that it could be seen from hundreds of kilometers away. And yet, even Tsar Bomba was small compared to what nature can do without trying. The device released about 2.1 times 10 to the 17th joules, enough to power the entire world for nearly a week, but a single large volcanic eruption or a moderate solar flare can exceed that. The energy from a supernova leaves it so far behind that it becomes difficult to even plot them on the same scale. When you think of it that way, our nuclear experiments are less a claim of dominance over nature and more like a rehearsal on a very small stage. They are proof of concept that the energies in the heart of matter are real and that we can briefly and dangerously set them free. But they also remind us how vast the steps are between human engineering and cosmic events. In this way, the leap from a campfire to Tsar Bomba is not unlike the leap from lightning to a supernova. The processes are related, rearrangements of matter releasing stored energy, but the scale changes the meaning. A campfire warms a few people. A nuclear bomb reshapes a landscape. A supernova can sterilize an entire star system. For all the power we've tapped, we've only managed to scratch the surface of the energy bound up in the universe. The sun converts about 4 million tons of mass into energy every second, quietly, steadily, without fanfare. It's been doing this for billions of years, and will keep doing so for billions more. Every photon of daylight on your skin is the product of nuclear fusion deep in its core. Our bombs are loud and brief. The sun's fusion is quiet and patient. Still, there is something sobering about the fact that we've learned to use this principle at all. We've used it for destruction, yes, but also for peaceful purposes. Nuclear power plants that heat water and turn turbines. Research reactors that make isotopes for medicine. It's a reminder that energy itself is not moral or immoral. It's a tool, and what we do with it says more about us than about the physics. As we move onward in our journey up the scale, we'll leave behind these human-made sparks and look at the forces the Earth has been using since long before we arrived. Because while our bombs are the brightest bursts we've made, the planet beneath us has its own ways of rearranging matter and releasing energy, and those ways make our devices seem almost gentle. They can shake continents, blot out the sun, and alter the climate of the entire world. When we stand beside a volcano and feel the ground tremble, we're reminded that we live on a thin crust floating over a sea of molten rock. The pressures that build there are patient. They take centuries to prepare their release, but when they finally act, they do so with a power we can't control or match. In the next step of our journey, we'll stand quietly near some of the most famous of these events, not close enough to be in danger, but close enough to feel the scale, and see how even here, on our own world, nature works with a hand that can move mountains in a single gesture. If you've ever boiled water with a lid on the pot, you've seen the first, most domestic version of what drives volcanoes. The water begins to stir as it heats. Tiny bubbles form, rise, and break. Steam builds up under the lid, rattling it gently at first, then harder, until you lift it to let the pressure escape. That's the safe kitchen version. Now replace the pot with a mountain, the water with molten rock, and the gentle hiss of steam with a shock wave that can be heard hundreds of kilometers away. This is the scale at which the Earth sometimes chooses to move its stored energy from deep underground into the open air. Most of the time, volcanoes are slow talkers. They ooze lava that creeps down their slopes in slow rivers, glowing in the dark. They build their mountains grain by grain, cooling rock into new layers. But every so often, one of them decides to speak all at once. The pressure under the crust has been building for years, even centuries, and when it finds a weak point, the release is sudden and absolute. One of the largest voices in this conversation is Yellowstone. Today it is a national park with quiet geysers, mineral pools that shimmer in blues and greens, and herds of bison wandering over open meadows. But beneath it lies a magma chamber large enough to make the whole region rise and fall like a breathing animal. 3 times in the last 2 million years, that chamber has emptied itself in eruptions so vast they changed global climate. Ash from those events has been found across most of North America. If Yellowstone were to erupt on that scale again, the sky over continents would dim, temperatures would fall, and the world would remember that the Earth can act on planetary terms without our help. Other volcanoes have done this within recorded history. In the year 1815, Mount Tambora in Indonesia erupted with a force unmatched in more than 1,000 years. It hurled ash and sulphur high into the stratosphere, where they spread across the globe, scattering sunlight and cooling the planet. The following year became known as the Year Without a Summer. In New England, snow fell in June, crops failed in Europe, famine followed in Asia, all of it traced back to one point on a map, where the Earth opened its lungs and exhaled a cloud that circled the world. In 1883, Krakatoa, another Indonesian volcano, exploded so violently that the sound was heard 3,000 kilometers away. The pressure wave travelled around the Earth multiple times. The sunsets of the following months were painted in extraordinary reds and purples, as fine ash in the atmosphere bent sunlight into new paths. Painters tried to capture them, writers tried to describe them. But the truth was stranger than any description. The sky itself seemed to remember the eruption and retell it in colour each evening. It's not only the blast and the ash that changed the world after such eruptions. Tsunamis can follow, born from the sudden collapse of volcanic islands into the sea. The Krakatoa eruption sent waves tens of meters high into nearby coastlines, sweeping away villages before the ash had even begun to fall. These are the chain reactions that remind us that the Earth systems are deeply linked. Air, water and rock all moving to the same rhythm when stirred hard enough. For all their danger, there is also a certain stillness in a volcano before it erupts. In the minutes or hours before, the air can feel unnaturally calm, the birds silent, the wind absent. Even those who do not know the science can sense that something in the ground is gathering itself. And then, without warning, the calm is broken by an upward force that seems almost impossible. The Earth throwing part of itself into the sky. If you stood far enough away to be safe, you might be able to watch it the way you would watch a thunderstorm, with a mix of awe and humility. The eruption column climbs like a tree made of smoke, its branches spreading at the top where it meets a stable layer of air. Lightning can flicker inside it, sparked by the friction of ash particles colliding. Below, pyroclastic flows, surges of gas and ash, race down the slopes faster than a human can run. In the days after, the sunlight can look different. The warmth on your skin feels muted. The colours around you shifted towards softer tones. The ash in the atmosphere scatters the blue light, leaving the world tinged with gold or orange even at midday. And if the eruption is large enough, that change in light can last for years, altering not just sunsets, but seasons. When you compare these events to the nuclear explosions we've made, the contrast is striking. Our bombs are bright, brief, and sharply defined in time and space. A super eruption is slower in its unfolding, but far greater in its reach. The effects ripple outward for months, touching oceans, winds, and climates in ways no single device could match. They are reminders that the planet's own reserves of energy, stored in the slow churning of its mantle, are beyond our engineering. There's a kind of quiet poetry in this. The same earth that grows forests, shapes rivers, and keeps a steady climate for centuries also holds within it the means to reset the balance in a single, decisive gesture. We live on the cooled crust of a restless heart, and now and then it beats harder. In the rhythm of our journey, volcanoes are the bridge between the familiar scale of human action and the vastness of the forces beyond. They reach higher than our tallest buildings, move more mass than our largest machines, and alter more lives than our greatest inventions. And as we step upward toward the sun in the next part of our story, it's worth remembering that these events are still small when measured against what stars can do. A volcano can change the colour of the sky. A star can change the shape of the sky itself. The sun does not look like it has moods. From here on Earth, it seems steady. A white gold disk that rises and sets with the same calm precision every day. But if you could watch it up close, you would see that its surface is never truly still. Granules the size of continents ripple and vanish in minutes. Dark sunspots appear and fade like bruises. Loops of glowing plasma arch into space, rising and falling in arcs thousands of kilometers high. And sometimes those loops snap. Inside the sun's atmosphere, magnetic fields twist and coil like invisible ropes. Most of the time they stay wound together, guiding the charged particles that stream along them. But as the sun turns and the fields tangle, stress builds. Imagine twisting a rubber band tighter and tighter. At some point it can't hold its shape any longer. In the sun, when that breaking point is reached, the magnetic structure reorganizes itself in an instant. The result is a solar flare, a sudden burst of energy and light across the spectrum from radio waves to X-rays. To the human eye, a solar flare would be dazzling. In just a few minutes, it can release more energy than billions of nuclear bombs combined. If the sun's surface is a calm sea, then a flare is a superheated geyser erupting upward, carrying with it the evidence of magnetic knots snapping free. The light travels to Earth in 8 minutes, but the particles, protons and electrons accelerated near light speed, can arrive in less than an hour. When these particles reach our atmosphere, they set off a chain of reactions. The upper layers of air become ionized, bending and distorting the paths of radio waves. Satellites in orbit can experience sudden surges of current in their electronics. Astronauts outside the protection of Earth's magnetic field must take shelter. And near the poles, where the magnetic shield funnels particles downward, the sky glows. The aurora is the gentle face of a solar storm. Curtains of green, red, and violet light ripple across the night, shifting as if stirred by an invisible wind. To see them is to watch the atmosphere itself become a painting, each colour born from particles colliding with oxygen and nitrogen high above the ground. They are, in a way, the sun's apology, a gift of beauty after a moment of violence. But not all solar outbursts are limited to flares. Sometimes, the Sun throws out a much larger piece of itself, a coronal mass ejection, or CME. This is not just light and high-speed particles, but a cloud of plasma weighing billions of tons, threaded through with magnetic fields of its own. When a CME is aimed at Earth, it can compress our planet's magnetic field like a ball pushed into water. Currents are induced in long power lines, transformers overheat, and entire grids can fail. In March of 1989, such an event struck Earth and knocked out the power grid in Quebec for 9 hours. The same storm pushed the aurora as far south as Texas. In July of 2012, a CME even larger than that one crossed Earth's orbit, but we weren't there. The planet had moved on in its yearly path, and the plasma cloud passed harmlessly by. Had it struck, the damage to our technology could have been severe, perhaps lasting months. The most famous such storm in history happened in 1859, the Carrington event. Telegraph operators reported sparks leaping from their equipment. Some were able to send messages even with their power supplies disconnected, the lines themselves carrying the induced currents. In the nights that followed, aurora lit up skies across the world, bright enough to read a newspaper by. Events like that remind us that the Sun, for all its warmth and steadiness, is not a perfectly predictable companion. It has cycles, roughly 11 years from quiet to active and back again, and within those cycles, sudden moods. It can go from gentle to fierce in a matter of minutes, and its reach extends far beyond the orbit of the Earth. The solar wind, a constant outflow of charged particles, carries its influence all the way past the edge of the solar system. Still, there is something reassuring in knowing that we've been living with this temperamental star for all of human history. Its flares and storms have come and gone, and though they can trouble our machines, they have also given us nights of rare beauty. The aurora is a reminder that even in the most violent processes, nature leaves room for wonder. In the scale of our journey, solar flares are a significant step upward from volcanoes, but they are still modest compared to what the largest stars can do. There are suns out there far bigger than ours, burning hotter, shedding their outer layers in winds that carve whole regions of space into vast glowing shells. Some of them exist in pairs, their winds colliding like ocean currents meeting in a narrow channel, stirring up storms of their own. And those winds, in turn, are only part of the prelude to the even greater transformation still ahead. So before we leave our familiar yellow star behind, we'll take one more step outward, into the company of those other, more extravagant suns, to see how they shape the space around them with nothing more than the force of their breath. Our Sun, for all its moods, is a gentle star by galactic standards. It burns steadily, with flares that are impressive to us but modest on the cosmic stage. Out beyond our neighbourhood, there are stars that live faster, burn hotter, and spend their short lives throwing themselves into space with a ferocity our Sun will never match. One of the most remarkable kinds is called a Wolf-Rayet star. They are massive, bright and unstable, the bare hearts of former giants, their outer layers already stripped away. What remains is a core so hot it glows in intense ultraviolet, driving a stellar wind that can be millions of times stronger than the wind from our Sun. If you could stand near one, though you couldn't, because near, in this case, would still mean millions of kilometres away, you would see that wind not as moving air but as a constant flow of particles, racing outward at thousands of kilometres per second. These winds are not invisible. Over time, they push surrounding gas and dust into vast glowing bubbles. Astronomers have taken images of them that look like delicate soap films stretched across the starscape, illuminated from within. The shapes can be spherical, like lanterns in the dark, or twisted into arcs and filaments by the movement of the star itself. In a few tens of thousands of years, the blink of an eye in cosmic terms, these winds can hollow out entire regions of interstellar space, sweeping them clean for hundreds of light years around. And then there are the blue supergiants. They are some of the largest and hottest stars known, luminous enough to be seen from across galaxies. Their winds are not as fast as those of Wolf-Rayet stars, but they are still thousands of times stronger than our suns. In the dense stellar nurseries where these giants are born, their combined winds can shape entire clusters, carving out cavities and triggering new rounds of star formation in the compressed gas at their edges. Sometimes, a massive star does not live alone. In certain binary systems, two stars with strong winds orbit each other, and where their winds meet, a new kind of storm begins. Imagine two powerful ocean currents colliding head-on. The turbulence, the standing waves, the roar. In space, the collision zone between two stellar winds can be a place of intense heat, where particles are accelerated to high energies and X-rays are produced in abundance. Astronomers detect these collisions as bright points of radiation, flickering in step with the star's orbits. The shapes of these wind collision zones can be surprisingly graceful. In some systems, the winds wrap into spirals, traced out as the stars circle each other. In others, they form long, curved shock fronts that stand between the two like an invisible wall. The patterns depend on the relative strengths of the winds, the distance between the stars and the speed of their orbit, a reminder that even in the most chaotic environments, structure finds a way to emerge. For all their strength, these winds are only one stage in the life of a massive star. They are the slow prelude to the main event. In the end, these stars will exhaust their fuel, their cores will collapse, and the result will be something far more violent, a supernova, perhaps even the birth of a neutron star or black hole. The winds are in a sense a rehearsal for that final act, carrying away mass and shaping the star's surroundings so that when the explosion comes, it plays out on a stage the star itself has prepared. Compared to what we've seen so far, these winds might seem quiet. There's no sudden flash, no immediate disaster. They are constant, patient forces, but their patience operates on a scale that can move light years of material and alter the future of entire star systems. And in the slow flow of our journey, they serve as a bridge between the steady, nurturing wind of our sun and the far more dramatic changes that happen when stars reach the end of their lives. In the glow of a Wolf-Rayet bubble, or the spiral of a colliding wind binary, you can see echoes of smaller patterns we've already visited. The shaping of clouds by wind recalls the shaping of ash plumes by volcanoes. The meeting of two stellar winds recalls the meeting of charges in a lightning strike. Two forces, approaching from opposite sides, finding a place to meet and transform. The scale has changed, but the rhythm remains. From here, our path will carry us toward the moments when stars stop giving and start collapsing, when the gentle push of a stellar wind is replaced by the unstoppable pull of gravity. Massive stars will swell into red giants, shedding their outer layers in great waves. Some will explode in Type 1 or supernovae, their light visible across the universe. And in the densest remnants we will find neutron stars, the next rung on our ladder, and the prelude to the collisions that can shake space-time itself. But for now, let's pause here, in the space between tempests. Imagine standing far enough away from a Wolf-Rayet star to see its bubble in full. The edges glow faintly, lit by starlight scattering off the gas. Inside, the star burns white hot, its wind streaming outward without end. Beyond that bubble, the starscape stretches into infinity, each point of light with its own story. And somewhere, not yet visible to us, two neutron stars are circling, drawing ever closer, their meeting still millions of years away. The moon feels like it has always been there, a constant presence in the sky, guiding tides, marking months, and quietly keeping watch as life on Earth changed from single cells to cities. But there was a time, deep in the planet's youth, when the moon did not yet exist. Back then, Earth was young and restless, Wrapped in an atmosphere of steam and volcanic gases, its surface still shaped by seas of molten rock. And somewhere in that wild early solar system, a wandering world the size of Mars was on a slow collision course with us. We call that world Theia. It did not come screaming in from the edge of the solar system like a comet on a brief visit. Instead, it shared much of Earth's orbit, drifting closer over millions of years. You can imagine the two worlds circling the sun like dancers moving in the same great hall, each on its own path, until one step brings them together in a slow-motion embrace that neither survives unchanged. When Theia finally struck, it was not the kind of impact you see in a movie. No single flash, no instant crater. It was more like two drops of liquid merging, but with a violence that ripped both apart. The crusts shattered, the mantles mingled, and a cloud of molten rock and vapour billowed outward into space. The heat was so great that much of the rock was not just melted, but vaporized, becoming a glowing mist orbiting the wounded Earth. Over the next months and years the mist cooled. Droplets condensed, clumped together, and began to orbit as a disk of debris. Within that disk the clumps merged, growing larger with each encounter. Eventually one body became dominant, sweeping up the smaller fragments, smoothing its own shape into a sphere. This was the moon's long gestation, hidden from any eyes, unfolding in the quiet darkness above a still recovering Earth. When it was new, the moon was much closer than it is now. The tides it raised were enormous, waves that surged far inland and then retreated, carving coastlines over and over. The Earth itself spun faster in those days. A day might have been only 6 hours long. Over billions of years, the tides have pushed the moon farther away, slowing Earth's rotation until it settled into the sky we know now, rising and setting with a patience that feels eternal. The moon's birth was not a one-off accident. Across the solar system, other worlds bear the marks of similar encounters. Mercury, for example, has a core that is far larger in proportion to its size than Earth's. One idea is that an early impact stripped away much of its outer layers, leaving behind a dense metallic heart. Uranus spins on its side, its poles where most planets keep their equators, perhaps the result of a colossal blow that tilted it into this permanent lean. And Saturn's beautiful rings may be the remains of a shattered moon, or a body that wandered too close and was torn apart by tidal forces. Even beyond our own neighbourhood, we see hints of such dances. Around distant stars, astronomers have found clouds of dust glowing in infrared light, signs of recent collisions between rocky worlds. Sometimes those collisions are gentle enough to merge two planets into one. Sometimes they are so violent that only fragments remain, scattered into a belt of debris. The same physics that shaped our moon is still at work, playing out over billions of years in systems we can only glimpse. It's tempting to think of collisions as endings, and in one sense they are. Theia no longer exists, at least not as an independent world, but they are also beginnings. Without that impact, Earth might have no moon, and without the moon, our planet's history would have been very different. The moon's gravitational pull stabilizes Earth's tilt, keeping our seasons from wandering wildly over time. It shapes the tides, which may have been important in nurturing early life. It gives us a nightlight bright enough to change the behaviour of animals, and a surface whose silent craters hold the record of ancient events long erased on Earth. In that way, the giant impact was not just a catastrophe, it was a sculptor's strike, knocking away what was to make room for what could be. When you look at the moon now, you're looking at a reminder of the day Earth was remade, and at the partner that has been with us ever since. From here, our path will leave these planetary waltzes and turn back toward the stars themselves. Some stars never grow bright enough to truly shine, caught between the worlds of planets and suns. Others burn brilliantly, then swell into giants before shrinking into dense white embers. Their lives, like the moon's, are shaped by the forces of gravity, motion, and time. only on a stage far larger than any planet could hold. Not every star ever gets the chance to shine. Some begin the long journey towards stardom but stop short, caught in a limbo between planet and sun. They are called brown dwarfs, a name that sounds plain, almost apologetic, but hides a story of quiet persistence. A star's life begins in a cloud of gas and dust, where gravity draws the material inward, pulling it tighter until it forms a sphere. As the sphere contracts, it heats up. For a true star, the heat and pressure in the core eventually reach the point where hydrogen atoms fuse into helium, releasing energy that pushes back against gravity's squeeze. That balance, fusion pushing outward, gravity pulling inward, is what keeps a star steady for millions or billions of years. A brown dwarf starts the same way but doesn't quite cross the threshold. It gathers material, grows warm, and for a time may even burn deuterium, a heavier form of hydrogen that fuses at lower temperatures than the regular kind. But deuterium is scarce, and once it's gone, there's nothing to keep the core hot enough for sustained fusion. The object cools, its light fading until only a faint glow remains, radiating away the heat of its birth. It's tempting to call brown dwarfs failed stars, but that's a little unfair. They aren't failures so much as different outcomes. If you picture a campfire that flares briefly and then settles into glowing embers, you have something of the right image. The embers don't fail to be warm, they simply live on a smaller, quieter scale. Brown dwarfs are more massive than planets like Jupiter, sometimes up to 80 times Jupiter's mass, yet still not enough to sustain the core conditions that a star requires. They drift through space, dim and often invisible to the eye, detectable mainly in infrared light. Some have atmospheres streaked with clouds made not of water, but of exotic compounds, iron droplets, molten silicates, materials that would be dust or rock on Earth. In their skies, these clouds can shift and swirl, creating weather patterns as strange as any in the galaxy. And though they are faint, brown dwarfs can still be dynamic in their youth. Many form with polar jets, narrow streams of gas shooting outward along their rotational axis, like the faint size of something that almost ignited but not quite. These jets, lasting only in the earlier stages, shape their surroundings, carving out small paths in the gas clouds from which they were born. If you could stand on a world orbiting a brown dwarf, not that such a world would be especially hospitable, you might see a sky with a permanent dimly glowing sun, its light more red or purple than white. The warmth would be gentle, more like the heat from a fading stove than the blaze of a true star. Nights would be long and cool, and the seasons, if there were any, would be subtle. Life here, if it ever arose, would adapt to a slow, muted rhythm. Brown dwarfs remind us that the universe is full of in-between states. Not everything fits neatly into categories. They're too hot to be planets, too cool to be stars, and too numerous to ignore. Astronomers estimate there may be as many brown dwarfs in our galaxy as there are true stars. They drift in the shadows, quiet, but not entirely dark. Their existence a reminder that cosmic evolution is as much about the almosts as the absolutes. In the grand story of stellar life cycles, brown dwarfs occupy the opening pages, the what-if scenarios that never become full chapters. But from here, our path will lead to stars that do make it, that shine for eons, and then grow old in ways both beautiful and dramatic. Some will swell into red giants, turning gentle light into a furnace that engulfs their nearest worlds. Others will die with sudden violence, scattering the elements for future stars and planets to inherit. And eventually, we will arrive at the stars that end not with embers but with collapse, shrinking into white dwarfs, neutron stars and black holes, each step a narrowing of scale and an intensification of power. But before that, there is the long, slow swell of a star approaching its end, and the luminous farewell it leaves in the night. Every star that burns hydrogen in its core is living in what astronomers call the main sequence, a long, stable middle age. Our Sun is there now, quietly fusing hydrogen into helium, keeping its size and brightness steady. But nothing lasts forever, not even this steady rhythm. One day the balance between gravity pulling inward and fusion pushing outward will shift, and the change will be slow at first, then impossible to ignore. The star will swell, growing many times its original size until it becomes a red giant. This is not a sudden explosion, but a long, graceful transformation. As the hydrogen in the core runs low, the star's centre contracts under gravity's pull. That contraction heats the core further, igniting a new phase of fusion in the shell around it. The extra heat pushes the outer layers outward, and the star's surface cools as it expands, turning redder in colour. From far away, a red giant can look almost serene, its light softer and warmer than before. Up close, the scale is staggering. If the Sun became a red giant today, its surface would extend past the orbit of Earth, swallowing Mercury and Venus, and perhaps even brushing the edges of our world. Planets that once basked in gentle daylight would find themselves inside the star's atmosphere, their surfaces scorched, their skies a continuous, burning red. And yet, even in this destructive phase, a red giant can be strangely beautiful. Its outer layers are not held tightly, they're puffed up and loose, stirred by slow, rolling convection currents the size of worlds. These layers drift outward over thousands of years, thinning as they go, until they form a vast glowing shell around the star. This shell, a planetary nebula, is lit from within by the hot core, shining in delicate colours shaped by the elements it contains. For a time, the red giant's life becomes a rhythm of pulses. Every few tens of thousands of years, the fusion in its shell becomes unstable, flaring briefly and sending a new wave of gas outward. These thermal pulses act like a heartbeat, each one expanding the nebula and enriching it with heavier elements forged inside the star. In their own way, these pulses are acts of generosity, seeding the surrounding space with carbon, nitrogen, and other building blocks of life. The planetary nebula that follows is short-lived by cosmic standards, fading over tens of thousands of years. But while it lasts, it can be one of the most intricate sights in the universe, glowing rings, delicate filaments, or even symmetrical shapes that look almost designed. The patterns are shaped by the star's rotation, magnetic fields, and sometimes by the gravitational influence of unseen companions. Eventually the star will shed so much of its outer layers that only the core remains. This dense remnant, no longer able to fuse anything heavier than carbon and oxygen, will become a white dwarf, a glowing ember cooling in the dark. But that is the next chapter. For now, we stay in the moment of the red giant's expansion, when the star is at its largest and most luminous, shining thousands of times brighter than before. If you imagine looking up from a nearby planet, one far enough away to survive, the sight would be overwhelming. The red giant would dominate the sky, filling half of it, its light filtering through your atmosphere in deep, coppery tones. Shadows would be long and soft-edged, and nights might never come fully dark. Even as the star neared the end of its life, it would bathe its surroundings in light and warmth on a scale far beyond its main sequence days. In the great flow of our journey, the red giant phase is both an ending and a giving. The star is dying, but in dying it enriches the galaxy, returning its elements to the cosmic pool. Every breath we take, every carbon atom in our bodies, has passed through a star like this. We are, quite literally, the product of such endings. From here, the story of a star can branch. Some white dwarfs will cool quietly for billions of years. Others, if they have the right companions, will go out in a sudden blaze, a type Ia supernova, scattering iron and nickel across space. But before that final act, we linger in the glow of the red giant, the lantern lit before darkness, the last great exhalation of a star that once burned steady and bright. When the last breath of a red giant drifts away, and the glowing shell of a planetary nebula fades into the dark, what remains is the star's heart, small, dense, and astonishingly heavy. This is a white dwarf, and though it no longer burns with fusion, it still shines with the stored heat of its former life. It is no larger than Earth, yet it can contain a mass comparable to the Sun's. Imagine holding a teaspoon of its matter. It would weigh as much as a mountain. A white dwarf does not have the roaring furnace of a living star. Instead, it glows like an ember left over from a great fire, cooling slowly over billions of years. Its surface can be hotter than 100,000 degrees at first, but without fusion, that heat steadily leaks into space. Over unimaginable spans of time, the glow will fade until the white dwarf becomes a cold, dark object, a black dwarf. But the universe is not yet old enough for any to exist. Every white dwarf we see is still in its cooling phase, still carrying the light of its past. There is, however, a limit to how much mass a white dwarf can hold before gravity overwhelms it. This is called the Chandrasekhar limit, named after the physicist Subrahmanyan Chandrasekhar, who calculated it when he was just 19. In simple terms, it's a weight limit even stars cannot exceed, about 1.4 times the mass of our Sun. Below that threshold, the white dwarf's internal pressure, created by the quantum rules that govern electrons, can support it against collapse. Above it, the balance fails. Sometimes, a white dwarf gains weight. If it orbits close to a larger star, it can pull in material from its companion. Slowly, that gas spirals down onto the dwarf's surface, adding layer after layer. For a while, nothing happens. The white dwarf simply grows heavier, edging closer to the limit. But when enough mass accumulates, the pressure and temperature in its outer layers become critical. In that moment, fusion restarts, but it does not restart gently. Instead, the entire star undergoes a thermonuclear runaway. Carbon and oxygen in the white dwarf's interior ignite all at once, and the result is a Type 1 supernova. In seconds, the white dwarf is unmade, its matter hurled outward at thousands of kilometers per second. The blast can outshine an entire galaxy for weeks, and in its light we can read distances across the universe. Type Ia supernovae are what astronomers call standard candles. Because they all ignite at roughly the same mass, they all release roughly the same amount of energy. By comparing how bright they appear to us with how bright we know they must be, we can calculate how far away they are. This is one of the tools that led to the discovery that the universe's expansion is accelerating, driven by something we call dark energy. The debris from such an explosion is rich in heavy elements. Iron, nickel, and other metals are forged in the blast and flung into interstellar space, where they will one day become part of new stars, planets, and perhaps life itself. Every iron atom in your blood was made in a star, and some of those atoms were likely born in the last moments of a white dwarf's existence. Not every white dwarf ends in such a blaze. Many live out their long cooling quietly, dimming until they disappear from sight. But even these quiet endings have their place in the cosmic story. They are markers of time, reminders of the billions of years it takes for a star to go from bright youth to dark, cold remnant. If you could stand near a white dwarf, again, ignoring the reality that its gravity would crush you instantly, the view would be strange. Its surface would be smooth and pale, glowing with an unblinking light. Space around it would feel empty and still, yet every so often, if it were in a binary system, you might see arcs of gas spiralling toward it from a companion star, like thin ribbons drifting across the black. In that quietness lies a certain dignity. The star has done its work, shone its light, given its elements, and now rests in the long twilight of its being. From here, our journey will turn to stars that die in more massive, more violent ways. Some leave behind neutron stars, objects so dense that their matter is packed tighter than an atomic nucleus. Some will merge, creating explosions that release gold, platinum, and uranium. And in the most extreme cases, they will collapse entirely into black holes, leaving behind only a region of space from which not even light can escape. The scale of energy we're moving toward is almost beyond imagining, but we will take it step by step, just as we have until now. Every massive star spends its life in a balancing act. Gravity pulls inward, trying to crush the star into the smallest possible shape, while the heat and pressure from fusion push outward, holding that collapse at bay. For millions of years, this contest goes on in perfect equilibrium. The star burns through its fuel step by step, fusing hydrogen into helium, then helium into heavier and heavier elements. Each stage is shorter than the last, like the beats of a clock that begins to tick faster as the spring unwinds. Eventually, in the largest stars, fusion builds up to iron, and here the process stops. Iron does not release energy when it fuses, it absorbs it. The star can no longer make more energy to hold back gravity. In that moment, the contest ends. Gravity wins. The core begins to collapse. This is not a slow process. In less than a second, the star's centre caves in, shrinking from the size of a world to the size of a city. The matter inside is crushed so tightly that protons and electrons combine into neutrons. The density becomes unimaginable. A teaspoon of this matter would weigh as much as a mountain. As the collapse happens, a flood of particles called neutrinos bursts outward. Trillions upon trillions of them pass through space, and through you, right now, almost without interacting with anything. In the collapse of a massive star, these neutrinos carry away most of the energy, leaving only a fraction for the rest of the explosion. The outer layers of the star, no longer supported, fall inward toward the core. They slam into it and rebound, sending a shock wave racing outward. For a brief moment, the shock stalls, struggling against the weight of all that material still falling in. But the neutrinos help push it forward again, and when it breaks through, the result is a supernova, a sudden blazing bloom of light and energy that can outshine entire galaxies for weeks. From far away, a supernova can look almost peaceful. It is just a new point of light appearing in the sky, growing brighter night after night before slowly fading. Up close, it is chaos beyond imagining. Layers of gas ripped away at thousands of kilometers per second, light pouring out across the spectrum, and a wave of newly forged elements rushing into space. Gold, silver, uranium, these too are born in the chaos. The core, now a compact sphere of neutrons, has become a neutron star. It spins rapidly, conserving the angular momentum of the massive star it once was. The collapse also amplifies its magnetic field, making it millions to trillions of times stronger than Earth's. This object, barely 20 kilometers across, has survived the death of a star and will endure for millions, perhaps billions, of years. If you could stand at a safe distance, which in truth might be dozens of light years away, you would see the expanding shell of gas glowing in intricate colours. You might hear, through instruments, the ringing of the neutron star's vibrations, or the rhythmic pulses of its rotation, and you would know that what you were seeing was both an ending and a beginning, the final chapter of a star's life, and the opening of countless new stories for the matter it left behind. In our journey, this is the threshold into extremes. We have seen white dwarfs, quiet and dense. Now we have neutron stars, denser still, wrapped in magnetic fields strong enough to shape space itself. From here, we will follow these objects into their varied futures, some spinning like cosmic lighthouses, others twisting space with their magnetic storms, and still others colliding to produce bursts of light so intense they can be seen across the universe. But before that, let us pause with the image of a collapsing star. The silence before the core gives way, the sudden rush inward, the neutrino storm and the shock wave blooming into light. In the end, the star's greatest act was not its long, steady burning, but this one, brief, final release. A moment when it gave almost everything it had back to the cosmos. A neutron star is a strange kind of survivor. Born in violence, it carries the memory of its parent star's collapse in every rotation, every ripple in its magnetic field. Though it is no bigger than a city, it contains more mass than our sun. Its surface gravity so strong that even light would curve slightly as it tried to escape. But what makes these objects especially remarkable is the precision, and sometimes the ferocity, with which they announce their presence. Some neutron stars become pulsars. These are neutron stars whose intense magnetic fields and rapid spins create beams of radiation that sweep through space like the beam of a lighthouse. If one of those beams crosses our planet, we see a pulse of light or radio waves. Each rotation of the star produces another pulse, steady and predictable. The fastest pulsars spin hundreds of times per second, yet they keep their timing with an accuracy that rivals the best atomic clocks humans have built. It is an odd thought. A dead star, no longer generating energy through fusion, still marking the passage of time with the steadiness of a heartbeat. In the dark spaces between the stars, these rotating remnants become cosmic metronomes, ticking away in radio bursts and X-ray flashes. Astronomers use them to navigate the galaxy, to test theories of gravity, and to detect the subtle stretching of space caused by gravitational waves. But there is another, more extreme branch of the neutron star family, the magnetas. If a pulsar is a lighthouse, a magneta is a lighthouse built inside a thunderstorm, its beams shaped by magnetic fields so strong they defy easy description. A magneta's magnetic field can be 1,000 times stronger than that of an ordinary neutron star, up to a quadrillion times stronger than Earth's. To put it in more human terms, if you stood halfway between the Earth and the Moon, such a field could still erase the magnetic strip on every credit card in your wallet. These fields are not just powerful, they're restless. They twist and snap, releasing sudden flares of X-rays and gamma rays that can outshine the rest of the galaxy for brief moments. On December 27th, 2004, one such flare erupted from a magnetar named SGR 1806-20, 50,000 light-years away. The burst was so intense that it briefly altered Earth's ionosphere, even at that immense distance. If it had been closer, the effects could have been much more dramatic. Yet despite their power, both pulsars and magnetars are quiet most of the time, their surfaces locked in stillness under the weight of unimaginable gravity. There are no earthquakes here, only starquakes, caused by shifts in the rigid crust under magnetic stress. These starquakes can rearrange the magnetic field in an instant, releasing energy equivalent to billions of nuclear bombs. And then, just as suddenly, the star falls silent again. From a distance, these neutron stars seem patient, almost contemplative. Their signals come at regular intervals, their flares are rare and brief, and their lives stretch for millions of years. But their very existence is a reminder of the extremes that nature can reach. They are the densest solid objects in the universe, balancing on the edge between matter as we know it and the collapse into something even stranger, a black hole. It is easy to imagine them as keepers of time in the dark. Long after our own clocks have stopped, their pulses will still sweep across space. Somewhere, in some future far beyond us, another civilization might detect those pulses and wonder what kind of mind could have built such perfect timers, not realizing they are listening to the remnants of a star's last breath. From here, our path will take us to events where neutron stars play the leading role in even greater displays of power, collisions that shake space-time itself, and flashes of gamma rays that, for a few seconds, outshine the combined light of billions of suns. We are moving toward the very edge of what physics can describe, but we will go there slowly, one step at a time, keeping our eyes on the quiet rhythm of these stellar clocks as they lead the way. Some events in the universe happen so quickly that, if you blink, you might miss them entirely. Yet, for the brief moment they last, they release more energy than the sun will produce in its entire 10 billion year lifetime. These are gamma-ray bursts, the brightest flashes known to science, and among the most mysterious phenomena we have ever studied. Astronomers first detected them by accident in the late 1960s. Satellites designed to watch for nuclear tests on Earth instead saw brief, intense bursts of high-energy radiation coming from deep space. At first, no one knew what to make of them. The bursts seemed to appear at random from all directions, and they never repeated from the same place. It was as if the universe was sending out random, one-time flashes, cosmic flares that were gone almost before we could register them. Over decades of observation, patterns began to emerge. The bursts came in two main flavours, long and short. The long ones can last from 2 seconds to several minutes, while the short ones are over in less than 2 seconds, sometimes just a fraction of a heartbeat. The difference in their length turns out to be a clue to their origin. Long gamma-ray bursts usually come from the deaths of massive stars. When such a star collapses, if it is spinning rapidly and stripped of its outer layers, it can form what astronomers call a collapser. The collapse funnels energy into narrow, ultra-relativistic jets that punch through the star's remains and into space. If one of those jets happens to be aimed at us, we see it as a gamma-ray burst, a brilliant, focused flash of energy, followed by a fading afterglow in X-rays, optical light, and radio waves. Short gamma-ray bursts, on the other hand, are often linked to the mergers of neutron stars, a meeting we will explore more closely later. When two neutron stars spiral together, their collision produces not only gravitational waves, but also a brief concentrated jet of gamma rays. The power released in that instant is staggering. In less than a second, the burst can radiate more energy than our sun will in its entire life. Both kinds of bursts are incredibly dangerous if you are close enough. Close in this context, meaning within a few light years. The gamma rays can strip away a planet's atmosphere, disrupt its climate, and even break apart molecules of DNA. Fortunately for us, such events are rare in our cosmic neighbourhood, and the narrow jets mean that most bursts are not aimed in our direction. From our safe vantage point, gamma-ray bursts are not threats, but tools. By studying their light, astronomers can peer into the distant past. Because they are so bright, we can detect them from billions of light years away, seeing events that happened when the universe was still young. In that sense, each burst is like a lighthouse beam, flashing from a remote shore, carrying a story from a time and place far removed from our own. To imagine one, picture a camera flash in a dark room, not the small pop of a handheld camera, but one so intense it lights up the entire building, the street outside, the city beyond, all at once. Then imagine that the flash comes not from a building, but from a star halfway across the observable universe, and that its light has travelled for billions of years to reach you. When you see it, you're witnessing something that no longer exists, its light the only trace left of its brief, furious life. The afterglow that follows a gamma-ray burst is just as valuable to science as the burst itself. As the jet collides with surrounding gas and dust, it produces a fading signal that can be studied for days, weeks, even months. These afterglows reveal the environment where the burst occurred, the composition of the material around it, and sometimes even the signature of freshly forged elements. And then, as suddenly as it appeared, it is gone. The place in the sky where it flashed returns to its former quiet, as if nothing had happened. But the record remains, in the data we have captured, in the maps of afterglow light, in the gravitational waves recorded when the burst came from a merger. We will return to these bursts soon, especially the short kind, when we follow two neutron stars on their final spiral into each other. There, the story will narrow from the scale of the universe's brightest flashes to the precise moment when matter, magnetism, and gravity produce both destruction and creation. But for now, we can hold in our minds the image of these two great types of burst, one born from a giant star's death, the other from the union of two stellar remnants, each a reminder that the universe's most dramatic moments can be measured not in centuries but in seconds. Far away, in a quiet corner of the galaxy, two neutron stars orbit one another. They have done so for longer than humanity has existed. Perhaps for hundreds of millions of years. Each is no larger than a city, yet each holds more mass than our sun. They are so dense that if you could somehow scoop a spoonful of their matter, it would outweigh a mountain. Around them, space is not empty but curved, shaped by their gravity into a deep well. Their dance is not a perfect circle. It is a slow spiral, a narrowing embrace. Every time they orbit, they lose an almost unimaginably small amount of energy, carried away by ripples in space-time, gravitational waves. These ripples travel outward at the speed of light, spreading across the universe. By the time they reach Earth, they are fainter than the width of a proton. Yet, with detectors like LIGO and Virgo, we can measure them. If you could translate those gravitational waves into sound, you would hear a deep, rising tone. At first, it is almost too low to notice, a bass note humming beneath the rest of the cosmic music. But as the neutron stars spiral inward, they speed up. The hum grows higher, faster, a faint chirp climbing toward its climax. This is space-time singing, the fabric of the universe vibrating under the strain of two of its most massive dancers. As the orbits shrink, the stars begin to feel each other's pull more strongly. The gravity is so intense that it distorts their shapes, raising bulges on their surfaces that always face one another. These tidal bulges are not like the gentle ocean tides on Earth. They are mountains of neutron matter, each one taller than Everest, rising and falling in milliseconds as the stars whirl around. The closer they get, the faster they move. In the final minutes, they circle each other dozens of times per second, hurtling along at a significant fraction of the speed of light. Space-time around them is twisted into a tight whirlpool, and the gravitational waves grow louder and more insistent. For billions of years, the two stars have been drawing together. Now, in their final moments, they close the last few kilometers in a heartbeat. From a safe distance, many light years away, the scene would be hypnotic. Two bright points, invisible to ordinary sight but blazing in gravitational energy, racing around a shared centre. You would see no flames, no sparks, just the smooth, inevitable tightening of their orbit, the slow turning of a cosmic key toward its final click. Yet if you could listen, you would hear that rising tone, that steady build in frequency, the music of a universe preparing for a note so loud it will echo across galaxies. LIGO and Virgo have caught this song before. In their long silent arms, mirrors shift by less than the width of an atomic nucleus as the waves pass through. To us, that tiny motion is proof that two massive objects far away have taken their final steps toward each other. It is the most delicate way to sense the most violent movements in the cosmos, and so the spiral tightens. Each orbit bleeds energy into space-time itself. The stars are no longer merely circling. They are falling, locked in a mutual pull neither can escape. When the distance between them is measured in tens of kilometers, they are so close that their edges nearly touch. The tidal bulges stretch, the gravitational waves scream at their highest pitch, and the speed reaches its peak. In one more fraction of a second, there will be no more orbits. The two neutron stars will meet. Their masses, their magnetic fields, their matter, all will collide in a moment that will unleash more power than any other explosion in the universe short of the Big Bang. The gold in rings, the platinum in satellites, the uranium that fuels reactors, all of it can be born in the fire that is about to erupt. But not yet. For now, in these last instants before contact, the spiral is all there is. Two objects locked together by the most fundamental force in nature, tracing smaller and smaller circles until there is no space left between them. It is the universe's slowest dance and its fastest race, the patient work of eons ending in the blink of an eye. For millions of years, the two neutron stars have circled each other. For minutes, they have whirled faster than the mind can easily picture. And now, in a fraction of a second, the space between them vanishes. The spiral becomes a single point. The moment of contact is almost incomprehensibly brief. The two surfaces touch at a relative speed close to a third the speed of light. The pressure where they meet is beyond imagining, so high that even the neutron matter, already crushed to the density of an atomic nucleus, is forced into new and unstable forms. Shockwaves ripple through each star, colliding and colliding again in the impossibly tight space between them. In that instant, their immense kinetic energy is released. Matter is flung outward in a vast expanding sheet, moving at 1/10 of the speed of light. This is not ordinary matter. It is neutron-rich debris, the raw material for the heaviest elements in the universe. In the chaos, atomic nuclei capture neutrons in rapid succession, forming gold, platinum, uranium, and dozens of other rare elements in what scientists call the R process. In the space of milliseconds, nature manufactures treasure on a cosmic scale. Enough gold, perhaps, to outweigh mountains, though it will be scattered thinly across light years of space. The collision also produces a blast of light, but not the familiar light we see every day. The first flash is in gamma rays, an intense, tightly focused jet that bursts outward at nearly the speed of light. If aimed at us, it would be one of the brightest things the sky could ever show, but most of the time, the beam points elsewhere. In this case, we imagine it shooting away into the darkness, visible only to distant observers in its path. What remains behind is hotter than the core of any ordinary star. The newly formed mass, part neutron star, part collapsing wreckage, may survive for a few moments as an overmassive neutron star, its magnetic field twisting and snapping in the turbulence. But soon it will likely collapse into a black hole, drawing in what remains of the matter around it. Yet the story is not over. The debris flung out by the impact is unstable. Its radioactive decay releases energy that turns the expanding cloud into a kilonova, a brief but astonishingly bright bloom of light. Over the next hours and days, this bloom will shine in optical and infrared wavelengths, brighter than 100 million suns before slowly fading. It will not last long, but while it does, it will be one of the most luminous objects in the galaxy. To watch it from a safe distance would be to see a flower opening in the dark. First, a faint glow, growing rapidly until it rivals the light of entire star clusters. The colours would shift as the elements within the cloud change, from a bluish-white early on, when the lighter R process elements dominate, to a deep red as heavier elements like lanthanides take over. All the while, the cloud expands, cooling and thinning, until the light finally fades into invisibility. The entire kilonova, from its first flash to its last fading ember, is over in about 2 weeks. But in that short time, it changes the universe around it. The elements it makes will drift into space, becoming part of future stars, planets, and perhaps even living things. The gravitational waves it sends will ripple through space-time for millions of light years. The light it produces will travel for eons, carrying the story of its birth into the far future. On Earth, astronomers who detect such an event do not see it in real time with their eyes. Instead, they catch its signals in instruments, the rising tone of the gravitational waves, the flash of gamma rays, the gradual brightening in visible light. Yet from those measurements, they can reconstruct the entire scene. The inspiral, the impact, the bloom. It is a detective story told in data, pieced together from the faintest whispers across the universe. For all its violence, the moment of contact is not an end, but a transformation. The two neutron stars do not vanish. They become something else, their matter and energy taking new forms, their story branching into new paths. And somewhere, perhaps billions of years from now, the atoms they created will be part of other worlds, perhaps even part of someone else wondering how they came to be. In the early morning hours of August 17th, 2017, the Earth was turning as usual. The sun was just beginning to rise in some parts of the world, while in others, the night sky still held its scattered stars. But in the quiet hum of the LIGO detectors in the United States and the Virgo detector in Italy, something unusual stirred. A ripple in space-time passed through the planet, stretching and squeezing it ever so slightly. The signal was faint but clear, a rising tone lasting over a minute, a signature unlike anything from black hole mergers. It was lower in mass, longer in duration. The patterns in the data hinted that the source was not a pair of black holes, but something lighter and smaller, two neutron stars spiraling together. It was a kind of event astronomers had hoped to see for decades, one that would open an entirely new way of studying the cosmos. Just 1.7 seconds after the gravitational waves reached Earth, NASA's Fermi Gamma Ray Space Telescope detected a short burst of gamma rays. The timing was uncanny. Two separate messengers, ripples in space-time and flashes of high-energy light, had arrived almost together, both telling of the same cosmic moment. It was as if the universe had spoken in two languages at once. This was the birth of multi-messenger astronomy. For the first time in history, scientists could both hear and see the same astrophysical event. Gravitational waves told the story of the inspiral, the gradual tightening of the orbit as the neutron stars lost energy. The gamma rays revealed the violent flash of the collision itself. Together, they painted a picture more complete than either could alone. Within minutes, alerts spread across the global astronomy community. Observatories on every continent and in orbit turned their eyes to the patch of sky where the signal came from. It wasn't easy. The location was broad at first, covering hundreds of times the size of the full moon. But slowly, as the data from LIGO, Virgo and gamma ray detectors were combined, the search area narrowed. In Chile, the SWOPE telescope at Las Campanas Observatory was among the first to spot it, a faint point of light in the galaxy NGC 4993, about 130 million light-years away. At first glance, it looked like an ordinary star, but over the next hours and days it changed, brightening, shifting in colour, then fading. This was the kilonova afterglow, the bloom in the dark that follows when two neutron stars collide. Over the next weeks, telescopes around the world and in space followed the fading light. The optical glow was soon joined by infrared observations, revealing the signature of heavy elements forming in the expanding cloud of debris. In the radio and X-ray bands, astronomers watched as the collision's shock waves ploughed into surrounding material. Every wavelength added a new layer to the story, like different instruments in a symphony contributing their own melodies. The data confirmed theories that had been forming for decades. The R process, the rapid neutron capture process, was indeed taking place in neutron star mergers, forging gold, platinum, and other heavy elements. The kilonova's colour evolution matched predictions. Even the tiny delay between the gravitational waves and the gamma rays was meaningful, offering clues about the physics of jet formation and the nature of space-time itself. It was not just a triumph of technology, though it certainly was that. It was a triumph of patience, of scientists around the world who had been waiting for this moment, refining their instruments, improving their models, hoping that one day the universe would provide the right event. And when it came, the response was immediate and coordinated, a kind of global dance in which every telescope played its part. In the months that followed, The event, catalogued as GW170817, became one of the most studied occurrences in the history of astronomy. Papers poured out by the hundreds. Its gravitational waves helped measure the expansion rate of the universe. Its light told of element formation and the behaviour of matter under extreme conditions. Even its host galaxy, NGC 4993, became a subject of fascination, with astronomers tracing its history and environment. For the public, the story carried a special resonance. The gold in rings and necklaces, the platinum in electronics, even the uranium in reactors. Much of it might have come from ancient collisions like this one. Somewhere in the deep past, long before Earth existed, two neutron stars had met, and their debris had drifted through the galaxy, eventually becoming part of a small blue planet. On that August day in 2017, humanity had witnessed such a creation in progress. It was a reminder that we live in a universe still making itself. Stars are still dying, elements are still being born, and the quiet night sky hides events of unimaginable power. The story of GW170817 was not just about what happened in a galaxy 130 million light-years away. It was about connection, about how the debris from such collisions becomes part of planets, oceans, and perhaps even people. And so, the first chapter of multi-messenger astronomy closed with a promise. There will be more. More ripples in space-time, more flashes of light, more stories told in two languages at once. Each will bring us closer to understanding the forces that shape the cosmos, and each will remind us that, even in the vastness of space, there are moments when the universe speaks clearly enough for us to listen. The collision has ended. The kilonova's light is still blooming outward, but at the heart of it, the story has already changed. The remnant, once a swirling mass of neutron-rich matter, can no longer hold itself up against its own gravity. It has crossed an invisible threshold. In the darkness, without fanfare, it collapses into a black hole. A black hole's formation is not like an explosion. It is more like a vanishing. One moment, matter exists as a thing we can describe. A star's core, a sea of neutrons, a place where magnetic fields and nuclear forces still define reality. The next moment, that place has gone beyond where we can follow. Its gravity has become so strong that not even light, the fastest traveller we know, can escape. The edge of this new territory is the event horizon, a border that can be crossed from one side only. From the outside, it looks like stillness, but inside, the laws of physics as we know them can no longer be guaranteed. Around this silent centre, the story does not stop. Matter flung outward in the collision arcs back under the pull of gravity. Instead of falling directly inward, it spirals, caught in a vast whirlpool. This is the accretion disk, a thin, rotating ring of superheated gas and plasma that glows with an intensity unmatched by any ordinary star. In that disk, particles crash together at incredible speeds, heating until they radiate in X-rays and beyond. What began as the debris of two neutron stars is now the fuel for the black hole's feast. From the poles of this spinning system, something even stranger can emerge. Under the right conditions, magnetic fields twist and snap, channeling some of the falling matter back outward in narrow-focused jets. These relativistic jets blast out at nearly the speed of light, cutting through the surrounding material. In the largest black holes, the ones millions or billions of times the Sun's mass, such jets can extend for thousands of light-years, visible across intergalactic space. Astronomers have photographed one in the giant galaxy M87, a brilliant needle-like stream like a cosmic lighthouse sweeping its beam into the void. Here, though, our new black hole is small by cosmic standards, perhaps a few times the mass of the Sun. Its jets will be brief, their light quickly fading. But the principle is the same. A black hole can be silent, swallowing everything without a sign, or it can be dramatic, lighting up the space around it as it feeds. Which one it becomes depends not on the black hole itself, for the black hole is only an emptiness, but on the matter that dares to come too close. To imagine it is to think of a whirlpool at sea. If the water is calm, the whirlpool is almost invisible, its pull quiet and hidden. But if waves or debris feed into it, spirals form, foam swirls, and the pattern becomes clear. The event horizon is like that invisible centre, always there, but visible only through what it does to the world around it. Over time, the black hole at the heart of this collision will settle. The kilonova's light will fade, the accretion disk will thin and cool, the jets will sputter and stop. What remains will be a patch of space that looks perfectly ordinary, until you measure it closely and find that light bends there in strange ways, that stars near its edge race faster than they should, that nothing crossing a certain invisible line ever comes back. And yet, for all the talk of destruction, a black hole is also a kind of preservation. The matter it consumes does not disappear in the deepest sense. Its mass, its energy, and even, perhaps, its information remain inside, folded into the very nature of the black hole itself. The universe does not erase easily. It transforms, it hides, it keeps its secrets close. In the larger scales, black holes are not only the remnants of collisions like this. They sit in the centres of galaxies, including our own, shaping the orbits of stars, stirring up clouds of gas, even regulating the rate at which new stars are born. They are not intruders, but pillars of cosmic architecture, silent anchors around which entire systems revolve. For now, the one born from this neutron star merger is a small addition to that vast family. It will orbit quietly within its home galaxy, invisible unless something strays too close. It will wait, not with intent, but with the inevitability of gravity, for the next chance to feed. It may never again have such a dramatic meal as the one that created it, but it does not need to. Time, to a black hole, is a patient thing. And so, after all the noise, the flashes, the waves that travelled across the universe, there is only stillness, a centre that cannot be seen, marked only by the way it shapes the space around it. The kilonova's bloom is fading, the jets are dimming, the feast is over, and the black hole rests in the quiet aftermath, holding the memory of the collision in its mass, if nowhere else. From the stillness around a single black hole, we now lift our gaze to the larger stage, where not just stars but entire galaxies move and change. In the vast dark between them they seem frozen in place, as though nothing could disturb their slow orbits around the cosmic web's invisible threads. But time is patient, and in the patient view galaxies are wanderers, and sometimes their paths cross. A galaxy merger is not like the crashing of two solid objects. It is more like two clouds of fireflies drifting together, each carrying a hidden centre of gravity. The stars themselves are so far apart that, in most cases, they pass one another without ever colliding directly. Yet gravity reaches across those empty spaces, reshaping the whole structure. As two galaxies draw closer, their arms distort, stretching into long tidal tails, streams of stars flung outward like ribbons caught in a slow wind. Wherever clouds of gas meet, the compression sparks new star formation. From our perspective, it might look like a sudden blooming of light along the edges and in the heart of the colliding shapes. Entire clusters of newborn stars may ignite in the span of a few million years, a blink in galactic time, but still long enough that we could watch the early stages if we returned again and again over centuries. At the heart of each galaxy, a supermassive black hole waits. These giants, millions or even billions of times the sun's mass, are far more massive than the newborn one from our neutron star collision. As the galaxies spiral together, their central black holes also begin to close in on each other. They may take hundreds of millions of years to meet, sending out ripples in space-time when they finally merge. these gravitational waves will be much longer and slower than those from neutron star collisions. A deep, slow bass, lined to the faster notes of stellar-scale mergers. From a distance, a galaxy merger is one of the most graceful motions in the universe. Over hundreds of millions of years, shapes twist and fold, star streams arc outward and fall back in, and two glowing cores wind closer together. The process is as intricate as a dance, but without choreography, guided only by the pull of gravity and the distribution of matter. We know this dance is not rare. The Milky Way itself has had partners in the past. Smaller galaxies drawn in, their stars now scattered among our own. And ahead of us, about 4 billion years from now, another meeting is certain. The Milky Way and the Andromeda Galaxy will begin their long spiral toward one another. From the scale of human life, that meeting is so far away it almost feels like fiction. But we can see the early signs. Andromeda is moving toward us at more than 100 kilometers per second, its light subtly shifted by the motion. Computer simulations let us watch the future in fast forward. The two galaxies approaching, their arms pulling into great arcs, tidal streams flaring outward until finally they merge into a single, larger galaxy, sometimes called Milkomeda in the playful language of astronomers. This future collision will not mean the end of Earth, though the night sky will change dramatically. For millions of years during the process, our sky will be filled with sweeping ribbons of stars from both galaxies, brighter than any Milky Way band we know now. The Sun, along with its planets, will drift into a new orbit in the merged galaxy, perhaps closer to the centre, perhaps farther out, depending on how the gravitational tides carry us. The thought of such immense changes can feel unsettling, but there is something comforting in their scale. These events move too slowly to disrupt our daily lives, or even the lives of civilizations. They remind us that we are part of a story that stretches far beyond our short chapters, a story written in movements so slow that entire species rise and fall before a single loop of the dance is complete. And when the dance is done, the new galaxy will be larger, brighter in some places, more diffuse in others. Its central black hole will be the product of two, its mass and influence grown. Around it, stars will continue to circle, and new generations will be born from the gas and dust left over from the merger. In time, the memory of the separate galaxies will fade, just as our own Milky Way hides the histories of the smaller systems it has already absorbed. From neutron stars to black holes to galaxies themselves, the universe repeats this pattern. Slow approach, deepening connection, and eventual union, followed by transformation. It is never quite the same after, yet nothing is ever truly lost. Matter remains, reshaped. Light continues, though it may take new paths. And gravity, the quiet choreographer, begins to look for the next partners in the endless dance. If galaxies are the great dancers of the cosmos, then cosmic rays are its restless wanderers, particles that refuse to stay still, racing through space at nearly the speed of light. They come from everywhere, at all times, invisible to our eyes but not to the instruments we've built to notice them. For most of their journey they travel alone, not as beams or streams, but as solitary messengers from distant and often violent events. The most energetic of them are rare, so rare that one might strike a square kilometre of Earth only once in a century. But when they do, they carry an energy that almost defies comparison. In 1991, a single proton, smaller than the width of a hair by a factor too large to count, hit the atmosphere above Utah with an energy of about 3 times 10 to the 20th electron volts. That's more than 1 million times the energy of particles we can accelerate in our most powerful machines, more than the kinetic energy of a baseball thrown at highway speed, all carried in something so small it could pass through a wall without leaving a mark. It became known, somewhat jokingly, as the "oh my god" particle. The name stuck because even physicists used to extreme numbers could only shake their heads at it. To reach that speed, it must have been pushed by some of the most extreme engines in the universe. Perhaps the shockwave of a supernova, the magnetic chaos around a supermassive black hole, or the jets from a gamma-ray burst. We don't know for sure, because along the way, the particle's path was bent by magnetic fields. By the time it reached Earth, its journey was too tangled to trace back to a single source. When a cosmic ray like this finally collides with our atmosphere, the meeting is not quiet. The particle smashes into a molecule of nitrogen or oxygen, and in that instant its energy is split among dozens, then hundreds, then billions of secondary particles. This is an air shower, a cascade of matter and energy spreading outward and downward like the branching pattern of lightning, except the branches are made of subatomic fragments moving at near light speed. Some of these fragments make it all the way to the ground, others decay in midair, producing brief flashes of light in the upper atmosphere. If you could stand in the darkness at high altitude and see in the right wavelengths, you might catch these flickers, small, silent bursts, each one marking the end of a journey that may have started in the heart of a galaxy millions of years ago. Cosmic rays are not only protons, some are helium nuclei, some are heavier atomic nuclei stripped bare. Many are far less energetic than the oh my god particle, born in more common places, the shock waves of supernova remnants, the turbulent magnetic fields inside our own galaxy, even the sun's eruptions. Those lower energy ones arrive constantly, passing through us by the trillions every day. They're harmless at that level, a quiet background to our lives, as much a part of our world as the sunlight and starlight we can see. For decades, scientists puzzled over how the highest energy ones could exist at all. The known laws of physics put limits on how particles can be accelerated, and the universe offers only a few places where those limits can be pushed to their extremes. Even now, every detection of an ultra-high energy cosmic ray feels like a note in a mystery, a reminder that somewhere, far away, something unimaginably powerful is still at work. We detect them not only with ground-based instruments, but also from space, watching for the faint ultraviolet glow of air showers from above. The Pierre Auger Observatory in Argentina covers an area larger than some cities with detectors spread across the plains, catching the rare moments when one of these cosmic wanderers decides to end its journey here. There is something quietly moving about the idea of a particle's path across the galaxy, perhaps across the universe, ending in the thin air above our heads. Its story is invisible to everyone but the instruments that register it, and even then it is only a whisper, a faint flash, a trace of charged particles, a brief electrical signal. And yet from those traces we reconstruct journeys that stretch across millions of light years, from unknown origins to the tiny patch of space we happen to occupy. If neutron star collisions and galaxy mergers are grand spectacles, then cosmic rays are like stray notes from those performances, carried away by the wind, travelling alone, arriving long after the music has faded. Some are ancient beyond imagination, others are young, sent on their way only years or decades ago. We catch them mid-flight, knowing we will never see where they began, but still grateful for the chance to meet them here, at the edge of their travels. And in that meeting, there's a quiet connection. For all their speed and violence, cosmic rays are also a reminder that the universe reaches us in many ways, not just in light we can see, or in waves we can measure, but in particles so small we could hold billions in our hands and never notice. The story they tell is unfinished, a thread we can follow only so far before it slips away. But even that glimpse is enough to remind us. There are forces at work out there beyond our sight, and sometimes, without warning, they send a messenger our way. Some parts of the universe show themselves only by what they do to everything else. Dark matter is one of those parts. Not truly dark, but invisible, refusing to interact with light in any way we can detect directly. It does not shine, it does not glow, it does not block the light behind it, and yet we know it is there. Because the visible matter, the stars, the gas, the galaxies, moves as if held in a deeper, invisible embrace. The first hints came from the way galaxies rotate. If only the visible matter were present, stars at the edges of a galaxy should orbit more slowly than those closer to the centre. But measurements showed they do not slow down enough. They whirl around as if bound by more gravity than the visible matter can supply. The missing mass, whatever it is, must outweigh all the stars and gas we can see, not by a small margin, but by a factor of several. Astronomers see its handprints elsewhere too. In galaxy clusters, the speed of galaxies moving within them demands far more mass than we can observe. On the larger scales, the cosmic web, a vast network of filaments and knots stretching across the universe, takes its shape from the pull of something unseen. Without dark matter, the filaments would be thinner, the knots weaker, the galaxies fewer. One of the clearest pieces of evidence comes from a place called the Bullet Cluster, a pair of galaxy clusters that collided hundreds of millions of years ago. The hot gas between their galaxies slowed down in the crash, heating and glowing in X-rays. But gravitational lensing, the bending of light from even more distant galaxies, showed that most of the mass passed straight through, hardly slowing at all. The invisible matter did not collide, it simply kept moving, leaving the luminous gas behind. If dark matter were only a trick of gravity or a miscalculation, this separation would not be so clean. What dark matter actually is remains a mystery. It might be made of undiscovered particles, too shy to interact with anything but gravity. It might be something stranger still, a property of space itself that we have not yet understood. We build detectors deep underground, shielded from cosmic rays, waiting for a rare interaction to whisper its presence. We watch the sky in radio, optical, X-ray and gamma rays, searching for patterns that might betray its nature. So far, it has kept its secret. And then there are ideas even stranger, theories that, while remote and perhaps impossible to test, stretch our imagination. One of these is vacuum decay, the notion that the universe's current state is only a temporary arrangement. In quantum field theory, the vacuum is not empty but filled with energy, the lowest possible energy state available. At least that's the hope. But if the state we live in is only a false vacuum, a slightly higher energy plateau, then there might be a lower energy state somewhere else. If such a lower state exists, and if a tiny region of space was somehow to make the transition, it could create a bubble of true vacuum that would expand at the speed of light. Inside, the laws of physics might be different. The strengths of forces, the masses of particles, perhaps even the dimensions of space. For anything inside the bubble, there would be no warning. The change would arrive as silently and instantly as the passing of a shadow. It is an unsettling thought, but almost every calculation suggests it is not a near-term danger. The timescales involved, if it is even possible, are longer than the age of the universe so far many times over. And even if it were to happen, there is nothing to be done. No way to predict, no way to prevent, no way to feel it coming. It is the sort of possibility one can acknowledge, in the same way one acknowledges the chance of a meteor striking the sun tomorrow. Logically possible, but so vanishingly unlikely that it need not disturb the quiet of the present. In a way, the very fact that we can think about such possibilities is part of what makes the universe remarkable. From lightning bolts above our heads to the most remote galaxies, from particles that pass through us without leaving a trace to invisible matter, shaping the largest structures in existence, we are able to gather clues and spin them into stories. Some of those stories we can confirm with observation. Others remain ideas waiting for a way to be tested. Both have their place, because even untested ideas can lead us to look in new directions. Dark matter with its silent pull and vacuum decay with its hypothetical transformation, sit at opposite ends of the spectrum of certainty. One is all but proven by its effects, yet unknown in form. The other is speculative, more a test of theory than a prediction of reality. Together they remind us that the edges of our knowledge are not a single line but a wide borderland, a place where what we think we know and what we can only imagine meet and mingle. And in that borderland there is a room for wonder. We can live comfortably with the knowledge that much of the universe is hidden, that some of it may always be hidden, and that our own place in it is small but aware. For all its shadows, the cosmos has given us light enough to see those shadows and time enough to keep looking. Before there were galaxies to merge or stars to collapse, before there were planets or even the atoms that make them, the universe was a dense, hot ocean of energy. No structures, no boundaries, no empty spaces between things, because there were no things yet. Time itself had only just begun its count. The first fractions of a second after the Big Bang were unlike anything we can experience, but we can trace their outlines through physics, a mix of theory and observation stitched together like a quilt of faint clues. In that first instant, the universe expanded at a rate so fast it almost defies language. Inflation, as we call it, was not the movement of matter through space, but the stretching of space itself, faster than the speed of light, not in defiance of the cosmic speed limit, but because the speed limit applies within space, not to the expansion of space itself. Imagine a speck of dust painted on a balloon, and then imagine the balloon growing so quickly that the dust loses sight of everything else painted alongside it. That's how entire regions of the young universe lost contact with one another, never to meet again. Inflation smoothed the wrinkles in that early ocean, spreading its energy evenly, while also planting the tiniest seeds of future structure. These seeds were quantum fluctuations, brief, random variations in density that, stretched to cosmic size, became the blueprints for where galaxies and clusters would one day form. They were imperfections, and it was those imperfections that allowed the universe to become interesting. A fraction of a second later, inflation ended. The universe kept expanding, but more slowly, cooling as it grew. The energy that filled it began to transform into matter, first into the simplest particles, then into protons and neutrons. For the next few minutes, the young universe became a kind of cosmic kitchen, combining those particles into the first atomic nuclei. This was Big Bang nucleosynthesis, and it happened with breathtaking speed. In less than 20 minutes, most of the free protons and neutrons had locked themselves into the first elements, mostly hydrogen, with about 25% helium by mass, and traces of lithium. Heavier elements would have to wait for stars to form, but the universe now had the basic ingredients for everything else to come. For hundreds of thousands of years after that, the universe remained a glowing fog. The nuclei were there, and electrons too, but it was still too hot for them to join together as atoms. Photons, particles of a light, bounced constantly from particle to particle, unable to travel freely. It was as though the cosmos were lit from within but covered in a thick opaque mist. That mist cleared when the universe cooled enough for electrons to settle into orbit around nuclei, forming the first neutral atoms. Suddenly, light could move without constant scattering. This moment, called recombination, was the day the universe made light in the sense we can still see today. The glow from that time still fills the cosmos, stretched by billions of years of expansion into the faint microwave radiation we call the cosmic microwave background. Every direction we look, it is there, a soft afterimage of the universe's first clear view of itself. That ancient light tells us the universe's age, its composition, its shape. It shows us the seeds left by inflation, now visible as tiny temperature differences across the sky. Those seeds would grow over billions of years into the galaxies and clusters we see around us. In a very real sense, the Big Bang gave us the ingredients. but it was this release of light that began the recipe for the universe we inhabit. When you look at the stars tonight, you're seeing light that began its journey long after that first glow. Light born in the hearts of stars, filtered through nebulae, bent around massive objects. But somewhere, mixed into the background noise of every radio receiver, is that older light, the echo of the moment the fog lifted. It is the oldest thing you can see without leaving Earth, and it has been falling on our planet since long before there was a planet to catch it. To think about that is to imagine a kind of connection across time. The atoms in your body are heavier than hydrogen and helium, so they were made later, in stars. But the photons in your eyes, in the warm light of your skin, have always been moving through a universe shaped by that first release. It was the day the cosmos became transparent, the first sunrise that would never set. We often think of beginnings as quiet, seeds in the soil, the first breath of a newborn, the first word of a story. The beginning of the universe was not quiet, but it has left us something gentle, a sky full of ancient light, spread evenly enough that no one place in the cosmos is darker than the rest. The brightness has faded, stretched thin by expansion, but the memory it carries has not. It remains a soft glow in the background of everything. We have wandered far. We began with a spark, a flicker of lightning above our heads, and followed its thread out into storms on the sun, into the steady breath of giant stars, and past the long, slow waltzes of colliding worlds. We stood at the quiet graves of old suns, felt the spiral embrace of neutron stars, and watched galaxies drift into each other's arms. We traced the outlines of matter we cannot see, considered the whisper-thin chants of the universe changing in ways we cannot predict, and drifted back to the first light, when space itself was still young. Now, the path bends back toward where we are, here, this moment, this stillness. The universe is still doing all of those things we spoke of right now. Somewhere, lightning is brightening the clouds over a summer field. Somewhere else, deep beneath the crust of a quiet plain, a supervolcano's chambers are filling grain by grain with molten rock. The sun's magnetic threads are twisting, ready to snap and send a wave of light across space. In a distant galaxy, a pair of neutron stars is circling closer with every heartbeat, centuries away from their final meeting. Two galaxies far beyond our sight are stretching out tidal streams of stars, the beginnings of a merger that will take hundreds of millions of years to complete. You will never hear the sound of these things. They're too far, too slow, too silent for human ears. And yet they are happening all the same, woven into the quiet fabric of this exact moment, as much a part of now as the air you are breathing. It is strange to think that the stillness around you is not empty at all, but connected to movements and events across billions of light years. The walls of your room, the bed beneath you, the breath in your chest, all of it is made of atoms forged in ancient stars, scattered across space, then gathered here by gravity and chance. The gold in a ring, the iron in your blood, the oxygen in your lungs. Each of them began as the output of something vast and violent, long before there was an Earth to hold them. The universe is busy, but it does not hurry. It keeps to rhythms far slower than the tick of a clock. The light from some of the stars you see tonight began its journey when the first humans carved tools from stone. Other light has been travelling since before our planet was born. Even now, photons from the afterglow of the Big Bang are passing through the room you're in, stretched into invisible microwaves by billions of years of expansion, still carrying the memory of the universe's first clear breath. If you step outside on a still night, you might notice how the air cools on your skin, how the dark sky seems deeper the longer you look. Some of the starlight you see is already a kind of ghost. The star that sent it may have changed or vanished entirely since it left. But the light continues, carrying the past into our present. In that way, the sky is never just a view. It is a conversation across time. The things we have talked about tonight, kilonovae blooming like flowers in the dark, galaxies drifting together like slow dancers, particles racing through space for millions of years to find us, they are not separate from you. You're not a spectator standing outside of them. You're made of the same matter, held together by the same forces, subject to the same gentle pull of gravity that moves entire galaxies. And so, when you lie here in the quiet, you're part of the same universe you have been travelling through in your mind. Your heartbeat is a kind of clock, your breath a kind of tide. If you could zoom out far enough, you would see that this moment, your moment, is stitched into the same grand pattern as every supernova, every colliding star, every slow swirl of galaxies in the dark. We began with power, with forces almost too large to imagine, but here at the end the scale becomes small again. A single person, a single quiet night. The hum of a fan, the faint warmth of a blanket, the slowing rhythm of thought. The universe is still out there, doing all the things it does, but you don't need to chase it. It is already here, in you, in the atoms of your skin and the space between your breaths. So you can let go now, let the images fade, the ribbons of starlight, the glowing arcs of colliding galaxies, the shimmering aurora of solar storms. Let them drift into softer shapes, like dreams that are content to be half remembered. If your mind wants to wander, let it wander. If it wants to rest, let it rest. There is nothing in the universe that demands your attention right now. The universe will go on, stars will burn, galaxies will merge, light will keep travelling, all without your needing to hold it in place. You can put it down just for tonight. The story will still be here when you wake, and so we reach the end of our journey for now. Whether your eyes are still open or you're already drifting between waking and dreaming, thank you for being part of this quiet exploration. You're always welcome to return, to wander with me again through the strange, beautiful and peaceful corners of the cosmos. Sleep well wherever and whenever you may be.